I just wanted to remind you the general rules. Every one of us, we have 15 minutes. It's, as you have already seen, it's not that much as you have expected. So everybody are wanting to take 15 minutes, but you know that the conference presentation has not been presented if the author has not answered the questions. So the questions are obligatory, otherwise your presentation does not count. So keep in mind that you will have to answer the questions. In order to leave some time for the questions, I have this sign, 3 minutes are left, so you are more or less in time, but you have to hurry up if you are not at the end. It's better to jump to conclusions if you see this sign. But if you see this sign, this means that you have to stop now, because just 1 minute is left for questions. And if 1 more minute passes, then I will stop you, but then your presentation does not count. So keep that in mind. You are presenter?
Yeah.
You are late? You're supposed to come 7 minutes before.
Yeah.
Please upload your slides. So until our colleague is uploading the slides, Kim is the first, yes? And what he is presenting is the simultaneous estimation of direction of arrival, or angle of arrival, and time of arrival. Actually, it is the task for a conventional radar, because all the radars that are used for air traffic monitoring are doing this. But in Kim's case, it is somewhat different radar. First of all, it is for automotive application. And the second is, it is not pulse radar, but it is continuous wave, frequency modulation, continuous wave radar. And if conventional beamforming techniques are used, then the resolution is not as expected, and of course the processing is needed. Then there are super resolution techniques like music, and I think you have mentioned music somewhere, but music is not as good in processing time. So what they are trying to do is everything at once. Time of arrival estimation, time delay estimation, beating the conventional beamforming techniques, and beating the music and other super resolution techniques, and everything at the lower processing price.
Yeah.
Kim,
Yeah.
floor is yours.
Yeah, thank you. Yeah, good morning, everyone. Thank you for inviting to present my research topic. My name is Sang-dong Kim. I'm working for Digist in South Korea. My research, the topic title is low complexity joint time of arrival and angle of arrival parameter estimator using dimension reduction for FMCW radar system. My agenda is made of introduction, system model, conventional algorithm, the proposed algorithm, simulation, computational analysis, and experimental result, and finally, the conclusion. The radar is used widely for a variety of applications. Radar defines an object detection system that uses the radar waves to determine the range, velocity, and angle of object. Traditionally, radar is used for military system to estimate the enemy's motion. These days, the radar system application moves to aviation, drone, vehicle, medical system. Among radar system, FMCW radar is widely used. FMCW means frequency modulated continuous wave. The FMCW radar transmitted a linear chop signal and analyze the frequency of received bit signal using a dechopping receiver. Dechopping receiver means that the transmitted chop signal is multiplied with the received chop signal. Using the dechopping receiver, the bandwidth of received signal is reduced to the bandwidth of dechopped bit signal, regardless of the transmitted bandwidth. Therefore, the complexity of signal processing is significantly lower than that of the conventional pulse radar system, such as a routable radar system. This page shows that the FMCW transmitted signal specifically. The transmitted signal include the time-scaled equation 1. This means that the signal is changed the frequency shaping based on the time. To estimate the time delay of arrivals in FMCW radar, we analyze the frequency of the received signal. The frequency of a bit received signal is proportional to the delay time between the transmitted signal and the received signal. When we have two targets, the radar signal is reflected from two targets. Finally, we can obtain the two frequency sinusoidal signal using the dechopping receiver. This equation, the final the time of delays the FMCW received signal. To estimate the angle of arrival in FMCW radar, we need to receive the phase difference of array antenna. We can find the time delay information and angle information using equation 3 like this. Finding the frequency of information of each parameter accurately determine the performance of the FMCW radar. In estimation parameter, I show you the radar parameter estimation trend. Until 1990s, Fourier series is used for analog radar. Until 2000, DFT algorithm is used for data radar as a data beamforming. These days, music algorithm and esprit algorithm is used for super resolution radar. The music means the multiple signal classification. Esprit means the estimation of a signal parameter via rotational invariant technology. I show the comparison of the resolution based on the algorithm. The music algorithm resolution has a better performance than the FFT's resolution like this figure. I show you conventional music algorithm for two-dimensional parameter. We receive the signal in the case array equation 4. We stack the data from the first antenna array to case antenna array in equation 5. We make the spatial temporal covariance matrix using the equation 6. Finally, we can obtain the eigenvector using the EVD of covariance matrix equation 7. The signal eigenvalue is correspondence to the signal eigenvector. The noise eigenvector is correspondence to noise eigenvalue. Using the noise eigenvector, we make the 2D music the spectrum function like equation 8. However, the conventional 2D music algorithm has a huge complexity for portable FMCW radar system. So we need to propose the DFT music algorithm. We start to choose music equation, spectral equation, the 9. The denominator of 2D music spectrum equation can be rewritten like this. This equation means that we can separate 2 dimension to 1 dimension through dimension reduction equation 10. Like S and T matrix. When we estimate one dimension parameter, we obtain other parameter estimation jointly through 1D parameter estimation. I show you proposed algorithm specifically. Firstly, we determine the TOA by DFT algorithm. After DFT algorithm and the peak detection, we can obtain the TOA index the vector. Therefore, we obtain the estimated TOA direction vector using a TOA index vector, equation 12. To obtain the angle of arrival for each target, we make the AOA parameter estimation equation using TOA direction vector like equation 13. After AOA estimation equation 13 and the peak detection, we can obtain the AOA index and the final AOA parameter like the equation 14. In simulation result, To assess the estimation result of proposed algorithm, parameters are set like a table. We can see the snapshot of the time delay angle map is like that. We can know that the conventional and the proposed algorithm has a similar performance for single target and for two target. In case of computational analysis, to evaluate the complexity reduction by the proposed algorithm, we measure the CPU execution time in MATLAB the software. The complexity of the proposed method is at least 100 times lower than that of the conventional the 2D music algorithm in case of the antenna array 2. In experimental result, the evaluation of estimation performance of proposed method were carried out in an anechoic chamber located in Digist in South Korea. With 24 GHz carrier frequency, we produced the FMCW radar RF module with one TX channel and two RX channel. We can know that also that the conventional and proposed algorithm has a similar the experimental result. I show the conclusion. We proposed the low complexity of a joint, TOA and the AOA using dimension reduction for FMCW radar system. Conventional methods such as 2D music are not used in real-time system. In order to apply real-time radar system, we present the joint TOA and AOA with a combination of a DFT and the music algorithm. To assess the proposed method, we conducted the experiment using our development 24 GHz 2-channel RF module and measured the processing time by the CPU execution time. The processing time of a proposed method is at least 100 times lower than that of the conventional 2D music algorithm antenna array 2. The result confirmed that the proposed method has a relatively lower complexity, while the estimation performance of proposed one is similar as that of the conventional method. I finished my research topic. Thank you for listening.
Okay, colleagues, are there any questions? Then I can use my position to ask you my questions.
Yeah.
First of all, very simple one. If you are using the beat frequency, this means that you are filtering out this double frequency chirp.
Yeah.
This means that you are throwing away some information because some of the energy is filtered out. I mean this double frequency chirp. What do you think, how much the resolution in the angle sense and temporal accuracy, how do they suffer?
You mean the reduced energy by the dechopping receiver, right?
Yeah.
Maybe this dechopping system use the transmitted signal.
But you see,
yeah, right.
You are plotting it like this, but
Yeah,
actually,
yeah.
if you go into spectrum, you will see that there is double frequency chirp at the high
Yeah.
frequency, and you are filtering it out. This means that part of the energy that have been received, it was thrown away.
I think
How it affects what would have been achieved if you have processed in real time in the original frequency scale and in reduced frequency scale. Okay, we will discuss this later.
yeah, right. It is a very important issue, but I think that there is no any reduced energy using a dechopping receiver, but I don't explain exactly that. So maybe the later
No, it requires separate investigation.
Yeah, okay.
More questions? Then I'd like to add one more question from me. Probably I missed this information, but you are reporting the frequency.
Yeah, right.
The antenna array is already clear what configuration, and even you've done the experiments. So what is the resolution in sense of the range resolution and in angle resolution? What resolution you have been achieving?
You mean that what is the sensitivity? in case of
distance
ledger.
between two signals that you can distinguish as two targets.
Yeah, to target maybe in case of the time of the resolution, the resolution is the proportion to the we can obtain the how to the resolve the two target under the maybe the UNI the radar over there the maybe radar has the maybe 1 meter resolution the distance maybe we are located at the over the 1 meter. The radar can detect the two target, but you come inside here under 1 meters distance. Maybe the radar cannot resolve.
So that's the resolution. So what is the smallest distance between two targets that can be resolved?
Maybe
in time domain, so it is expressed either in seconds or in meters, and in angular domain, it is expressed in angles.
But maybe I use the superledger algorithm to resolve the more the resolution, but there is no any solution to obtain the more the accurate the result.
Okay,
Yeah.
thank you.
Yeah. Okay.
Next presenter is coming from Estonia, and it is Maxim Buchenko, and he is presenting more or less in the same field. It is sparse reconstruction method for separating cardiac and respiratory components from electrical bioimpedance measurements. At the first glance, it seems that those two presentations, they are detached, but actually the same iterative deconvolution methods are used for super resolution processing as Kim presented, and the same is in your case. So, floor is yours. Please tell us what do you do.
Good morning, everyone. Glad to be here. So my name is Maxim Butsenko. I'm coming from Tallinn University of Technology. I'm going to present our work on separating cardiac and respiratory components from electrical bioimpedance measurements by the means of sparse reconstruction method. So if any of you have so-called smart scales at home, which measure your body fat, then basically it's done based on electrical bioimpedance. And electrical bioimpedance also is very promising for the medical applications. Because they're non-invasive and very cost-effective. And not only body fat can be analyzed with the help of bioimpedance measurements, but also different cardiac activities, simple such as heart rate, or more complicated such as central aortic blood pressure waveforms. And they can be successfully used in clinical applications such as cardiology, emergency care, anesthesiology, and many more. However, extraction separation of cardiac and or respiratory components from electrical bioimpedance is quite complicated because the spectra is overlapped in frequency domain, and obviously there is severe noise and different movement artifacts that are present because person who has like the sensor on it always moves, and this movement artifacts they actually disturb measurements quite a bit. But to start with the proposed method, let's look at the general signal model. It's a simple sum of the sinusoid. So we have k sinusoids with the noise, and k in our case usually unknown number of sinusoids. So we don't know like how many sinusoids are there in the signal that we wish to analyze. And the conventional method for sparse reconstruction for this is to construct a dictionary which will consist of the columns of cardinate sinusoids. So each column in the dictionary D is basically one particular sinusoid with one particular frequency that we wish to analyze. And estimation problem is usually solved through the well-known lasso minimization, where basically this term tries to fit the dictionary to the measured signal, and the vector x is basically the vector of weight coefficients, which chooses the best candidates from the dictionary that represent this y in the best sense, considering squared L2 norm. However, the second term is the sparse penalty term, which basically applies the sparse penalty on the initial estimate, and in result, the solution that we get should be sparse, because otherwise, if we don't add this sparse constraint here, then this term may result in the situation where, in statistical sense, the best representation from the dictionary D is some sort of combination of the columns, of all the columns that we have in the dictionary D. So The sparsity constraints actually helps us to pick only small number of coefficients from the dictionary D, and it's basically the formulation of the famous philosophical O'Kane's razor principle. So the simplest solution is the best solution. However, this approach have a problem. Obviously, the more resolution you want to get from the estimate, the larger the dictionary have to be. So the more columns we have to put in the dictionary. However, the bigger the dictionary, the more the complexity. So we have to perform more calculations. If we choose to go with the coarse grid, meaning smaller dictionary, it means that we decrease the complexity. However, it's not reliable. It's not only with it missing on some resolution, but also if the frequency component in signal that we wish to estimate lies between two adjacent columns or frequencies represented by columns in the dictionary, then we might miss it because it lies directly between two components in the dictionary. So one might think, why not to use the iterative zooming? We start with the coarse grid and then select element of interests and then form the smaller dictionary around it. Well, yeah, it can be a solution, but however, we still end up with the grid mismatch because in the initial estimate, in the first step, when we start with small dictionary, still the problem exists that if the component that we wish to estimate lies between two grids in a dictionary, we still might miss it. Possible solutions include adaptive grid or atomic norm penalty. However, they have their limitation. For adaptive grid, the resulting solution won't be convex. Yeah, I forgot to mention that one very nice property of this formulation is that the solution will be convex, so meaning like when we achieving the local minimum, it also be the global minimum. So it's like a good property. With adaptive grids, the solution won't be convex, so there's no such guarantees. And with atomic norm penalty, it's quite nice. However, it's quite complex. So its formulation is complex, and therefore it limits the size of the problem that can be considered. So we propose to form the dictionary in a wideband way. So basically, instead of putting for each column in the dictionary to be one particular frequency, we basically form each element in the dictionary as the band spanning from one frequency to another frequency. So basically solving this integral. And we start with a small dictionary and then zoom into active parts of the spectra until the required resolution is reached. With formulating dictionary in that way, we can use this iterative zooming approach because we don't miss any energy estimate in the first step. We don't miss any off-grid components. And that results in reliable estimation with decreased computational cost. So here we show the two different dictionaries, narrowband dictionary, a wideband dictionary. So wideband dictionary is depicted with a blue line, and the combination of two adjacent components from the narrowband dictionary, the red ones, are combined as a green line. So we see if, for example, the component that we wish to estimate lies on the frequency 0.49, then inner product with it will be 0, and basically we're going to miss this component. But it's not the case with the wideband dictionary because we still have energy here. So in terms of complexity, for the same resolution, we can expect as high as complexity reduction as high as 30 times for the wideband dictionary. And let's see how it fits to the considered problem of extracting the cardiac and respiratory components from the bioimpedance measurements. So we formulate the signal like that. So it basically consists of cardiac component and respiratory component. Obviously, noise is added. And if we assume that both components can be well approximated by the sum of sinusoids, so this combination, then we can reconstruct the signal back from the measurements by two dictionaries, cardiac dictionary and respiratory dictionary. K here is known because we only know that we only deal with two signals. So the dataset that we considered is based on measurements that were recorded in clinical conditions by using Circmon device provided by German Medical Estonian company. Operating frequency was 30 kilohertz. Initially, the bioimpedance signal was sampled at sample rate of 1 kilohertz and then further decimated to 200 hertz. And at the same time, when bioimpedance measurements were conducted, we also collected the electrocardiography measurements for further comparison between those. And the results of the reconstruction of bioimpedance signal showed with the red line. The blue line is the initial bioimpedance signal. They are quite close. And second part was to estimate the fundamental frequency of the cardiac component, basically track heart rate, and that's estimated with the blue line compared to the ground truth of ECG. And to conclude, in this work we present novel method for reconstructing signal components from bioimpedance measurements. And the method that we presented was based on the wideband dictionary formulation, which provides reliable estimate for parameters of considered signal with reduced computation complexity. For the future work, we know there are a few corner cases that still have to be solved. For example, half fundamental frequency problem. That is the problem when the signal under estimation can be well represented with the components that correspond to the signal which lies in the half fundamental frequency of the considered signal, because every other harmonic component in the signal will coincide with the actual signal. So therefore, sometimes algorithm can pick on the signal. So that has to be solved in the future, and then we are planning to instigate a hardware prototype for this method. Thank you for your attention.
Perfect timing, both of you. Congratulations, you are saving the other colleagues. Anybody would like to ask the question? Can I?
Sure.
What is confusing me, maybe I didn't get it wrong, is that you are reconstructing into sinusoids?
No, we reconstruct.
Every cardiac pulse is reconstructed not just as individual one, but
as sum of
treat
sinusoids.
all signal as sum of
As
the
sum of
sinusoids.
sinusoids, yeah, because if you look at the spectra of cardiac components, it's actually quite harmonic.
Yeah, I understand.
So
I've never done this because we usually try to treat the individual pulse as such.
Yeah.
So is it hard to model the cardiac pulse itself? To make some model, for instance, in radar case, we use Gabor function. Gabor function is Gaussian envelope sinusoid.
It certainly can be done, because this method that I described, right, the sparse reconstruction based on loss minimization, it actually doesn't have to be, the dictionary have to be, you can put Gabor elements there, you can put Haar wavelets, like whatever the best represents signal. And it's actually whole other field of research called online dictionary learning, when you actually learn the elements of the dictionary from the signal itself.
Because then you can tell what is the distance between two cardiac pulses immediately, which means that you are able to track the heart rates within one beat.
It's actually a good idea, because we started with a very simplistic approach, like just to check if it's possible at all to put this method to this problem. But different candidates that we can consider for dictionaries, yeah, sure, the field is limitless. But I think it's a good thing to check.
Thank you. Any more questions? Yes, please.
Well, I think you are working with a non-stationary signal, but you treat it as a stationary one, because you try to approximate your signal with the sinusoid components.
Mm-hmm.
So, do you think maybe it would be better to apply something different than the sum of sinusoids in order to approximate your signal?
That's exactly what we currently talked about. I mean,
So maybe I didn't get the point, but you were talking about the sinusoids.
Yes.
Yeah.
Good
point, yes.
In the beginning, I mean, that's the conventional approach. Actually, the approach we chose is to decompose the spectra into the bands of the spectra, and then estimate energy in each particular band, and not the sinusoids. Sinusoids is the conventional method for the sparse reconstruction.
But more or less the note is the same. The frequency is varying quickly, so treating it as more or less Fourier transform suitable signal.
If you actually consider that cardiac components, that's quite low frequency signal. I mean, it doesn't vary that much. So, but however, yeah, it's a valid concern, I guess.
Thank you. Anyone else? Then thank you.
Thank you very much.
Good timing and very good presentation. Then we're going back to radar applications, and this time radar is applied somewhat strange way, yes. Somebody needs to measure the faults in a bearing, then the machinery that rotates, and probably you know that from your car, for instance, yes, that if there is some strange noise coming, then the fault is coming. But their idea, Matsusada Reddy, is presenting the novel idea that they don't want even to touch the machinery, because the usual way is you attach the accelerometer to the case, but then you need to reach it, and it might be hot and might be not reachable. Yeah.
Yeah.
So your idea is to use the radar.
Yeah.
So please present what did you do.
Yeah. Thank you, Chef, for introducing, and good morning to one and all. Myself, Madhusudan Reddy, and I'm a PhD student from India, and I'm here to present on diagnosis of bearing outer race faults using low-cost non-contact methods with wavelet transforms. And my presentation goes like objectives, classification of faults, and principle and framework, experimental results, and conclusion. And the main objective of my presentation is to diagnose the bearing faults in the squirrel cage induction motors, and we want to propose a method which can able to provide the solution for fault identification with minimum cost and as well as a simple and without disturbing the working conditions of the machine. And coming to the various faults which will be occurring in the squirrel cage induction motors, there will be basically two kinds of faults, which will be electrical faults and mechanical faults. And in this, stator faults and rotor faults comes under the electrical faults, and mechanical faults is, which is a major one, is the bearing faults. And coming to the overall fault which will be occurring in the squirrel cage induction motors, generally rotor bar faults will be causes for 10% of the machines to fail, which is almost a minimum which is causing for the failure. And the next major one is the stator faults, which is almost 37% of the overall contribution. And in this, these stator faults can be able to manage or can be reduced once you could able to have a better winding as well as a better design of the stator. And the remaining one which is causing for the major failure of the squirrel cage induction motors is the bearing faults, which is almost 41%, and which we are trying to address in this presentation. And coming to the methods which will be utilized for the fault identification is can be considered as a contact methods and non-contact methods. And coming to the contact methods, generally they will place a sensor onto the machine and they will try to take the signal from that sensor like current, voltage or vibration, and by analyzing that signals they'll be identifying what kind of fault it is occurring in the machine. But with the problem with these kind of sensors attaching to the machine is these sensors will get damaged very soon because of the very heat which it is generated in the machine. So another kind of methods which can be utilized for the fault identification is non-contact methods, where they can able to identify the faults by using a thermal imaging or measuring flux or by using the acoustic measurement. But the difficulty with these methods is it will be get affected when there is other machines is surrounding. So this disturbance may causes for unwanted or false alarms for the fault identification. So we are trying to make a method which can be able to overcome all these difficulties. So my proposed method will be working basically on this principle, where when a microwave signal or a high frequency signal is projected onto a mechanically vibrating or oscillating machine or object, then the reflected signal will be gets amplitude modulated. If you could able to analyze that signal properly, then you can able to find out what and all frequency components are available, and with that frequency components we can able to get the fault information. So it's like this, where you will be projecting a high frequency signal onto the mechanically oscillating object, and once you receive that signal, so that signal will be amplitude modulated. And if you could able to get that signal information and can able to separate the various frequencies which is available, then we can able to identify the faults. And if it comes to the basic mathematical equations of how it can be done, so it's a very simple thing. What we'll be doing, it's a considers x of t1, which is a high frequency signal I'm projecting onto the machine, which is vibrating with a frequency of f2, and once it is get reflected and captured that signal, it will be amplitude modulated. And So that signal, if you could able to separate it, then you can able to find out the frequency components. So coming to the bearing faults, so bearings generally will be having all these 4 components like inner race, outer race, cage and other things, and each one will get possibility to get the damages like this. So in this we have just started with this work with the outer race faults alone. And as we know, any electrical machine or any machine, when it is in operating condition, definitely it will be having some vibration according to the supply frequency. So that is when it's a normal condition of operation, it will be vibrating with supply frequency, and whenever there is any fault occurs, according to that particular fault, the additional frequency component also will get added up, and that frequencies of the, whenever there is a bearing fault occurs, so this is the some frequencies which will be appearing in that signal. And this is my proposed method framework. So here from the UWB radar, it's a very small one which can be handheld, and that from that UWB radar I'm projecting the signal onto the machine, and that signal which will be captured and will be analyzed with the basic signal processing algorithms like FFT or STFT or wavelet, any signal analysis algorithms with which you can able to get the frequency information. And this is my experimental setup. So you can able to see it's a very small one, which can be a 2 centimeter by 2 centimeter, very small object which can be able to do this thing. And FFT, so when we do the FFT analysis, it's a basic thing. When we do the FFT analysis, here we are facing a difficulty that when it's the normal working conditions, so it could able to identify the things and all properly, but when it comes to the fault conditions, we could not able to distinguish much with this thing. So we tried with the STFT analysis, and here we could able to get rotor asymmetric frequency components, but when you go with the bearing fault frequencies, which it is generally appears at this range, is not very clear in this case. So we are trying to calculate the energy of this particular frequency component with which we can able to distinguish that whether it's some fault is happening or not. So that we tried with a wavelet. So this is how we will be calculating energy. And so when we tried with the wavelet analysis by calculating this, we have done with our MATLAB programming, and here generally these fault frequencies of the bearing will fall under the level 7, which is under normal condition we had a 4.72% of the total signal energy, and when it comes to the only outer race fault, we are getting it's around 4.82. And when it comes, and we tried one more with along with the outer race fault with the ball bearing fault also, so where the energy is a little bit increasing. So by comparing the energy, we are trying to estimate that there is some fault which is occurring in the bearing. And with this I'm concluding, and so we try to propose a method which is going to be non-contact, simple and low cost, and by comparing the energy levels we are trying to find out the fault what is happening, and proposed method it's able to overcome these difficulties. And still we need to do the multiple fault identification, because we have done still only with the bearing fault. We want to go with the still rotor bar faults and other kind of faults which need to be addressed, and as well as it need to be do for the automation, so that with even still now we are doing the analysis by manual, so that can be done by automatic, and you can able to address or give the alarm so that the person can able to make the required conditions. So this is some of the references, and thank you for listening.
Again, perfect timing. Congratulations, you managed, and you were not in a hurry and presented everything. So now we have time for questions. Anyone? Yes, please.
There was some patent application reference on the slides. Is it I didn't understand, is it your patent? Or
No, it's not mine.
Thanks.
More questions?
Okay, what is the resolution of your method? I mean, what is the fault that you can detect the smallest, I don't know, throw or something like that?
Actually, for this, we tried with a bearing with 1 mm of fault. The dimension of a fault on the outer race of the bearing is 1 mm. So that's what we tried.
More questions? Can I ask my
Yeah,
question? What surprised me at the very beginning that you are trying to use radar.
Yeah.
Because using the laser pointer and then mixing the signal that you receive and then getting the oscillations would have been much more easy, and the concentration of the beam is to the smaller spot, so you can check the spot on the machinery in that place, in that place, in that place. Why you have chosen radar?
Because if you take a laser, so maybe if you want to work with the daytime or some frequency disturbance may possible to get affected. So this what frequency might be good for us. That's what we have expected.
Okay. And one more question.
Yeah.
You are trying to explore amplitude modulation.
Yeah.
But actually, if you have the moving object, and everybody working with the radar would agree that you have Doppler shift, so it would have been easier to process the Doppler shift, because in order to get amplitude modulation, I could not imagine what phenomena should come into place to turn the vibration into magnitude modulation. But the Doppler shift, it is always there. And in all the applications that use non-contact vibration monitoring, they are using the Doppler shift. What was the reason for choosing the amplitude modulation?
That was a basic phenomenon what it was expected to work.
No, basic phenomena is Doppler shift. Okay, maybe that's the idea for future developments. Thank you very much.
Thank you.
Very good presentation. Thank you. And we are still in a radar field. One
Yeah.
more colleague is presenting on radar, but this time it is still same frequency modulated but continuous wave radar, but this time it is the application of the radar in surveillance. Young Song Jin?
No, I'm Jong Lee.
Ah, you are the last, yeah?
Yeah,
Jong Lee. So Jong Lee,
yeah,
floor is yours. Please
yeah.
tell us
Thank
on
you.
your developments.
Good morning, everyone. I'm Jong Lee. My paper's title is the design and implementation of a FMCW surveillance radar based on the dual chops. Co-authors Mr. Young Seok Jin, Dr. Bong Suk Kim, and Dr. Sang Dong Kim. I'm working for the radar lab. This is the South Korea. This is my contents to present. Introduction system model, and I will show compare the conventional and proposed detection algorithm. And I will show the simulation and experimental result, and I will end conclusion. Radar have many applications. Radar sensors have more reliable and more robust and higher detection performance than other sensors, such as the camera and infrared and the sound sensor. Radar have the two kinds, the pulse radar and CW radar. Pulse radar uses very short times pulse, and the CW radar, FMCW radar, transmit a continuous wave. And compared to the pulse radar, and FMCW radar had relatively low figure power and meet the certain range and velocity resolution required by using the simple hardware, the architecture. This is the cost-effective radar. And compared to the CW radar detects easily the Doppler shift, can detect, but it can't simultaneously the range and velocity. But the FMCW radar can detect the multiple core parameters like this, the range, velocity, and angle simultaneously. System model. This is the 1/k FMCW radar. 1 is the transmitter antenna, K is the receiver antenna. This is the transmit signal. F0 is the operating frequency, and the receiver signal, X subscript LK, L is the chop number, K is the antenna receiver number. Tau is the launch rate between the radar and the obstacle or target. And FD is the Doppler frequency of the target. And the theta is the degree of the angle of the target. And finally, we get the bit signal. And this is the analog form and the digital form. We can use the extracted bit signal. We can find the and calculated the range and Doppler velocity and position or angle. In this show, in the conventional detection algorithm, and we motivations in these papers. This is the in general the radar detection algorithm architecture. We use the 3D cuber, the bit signal, to extract the range and the velocity and angle of the target. The conventional algorithm performed to 3D FFT, fast Fourier transform, in the 3D data cuber in the time domain range, and the ramp, multiple ramp domain is the Doppler, extract the Doppler, and antenna array domain, we get the angle. However, this is the many data 3D cube FFT processing. We need the high power computing and the large memory size. In this paper, this is the motivation. We focused, we contribute to the how to use the complex of detection algorithm in the surveillance radar. This is our approach to how to reduce the complex in the surveillance radar. In surveillance radar, the top priority issue to make a decision whether any target exists or not, the presence of target. And to reduce the complexity, we approached it. We used only two ramps. This is the symbol transmitter FMCW signal symbol. Not all the chopped, instead only some dual chops while the performing FFT operation. This is the verbal concept. Solid line is the first ramp bit signal, and dashed line is the third ramp bit signal. You can see the same in the stationary target, really same. The difference, the bit signal between the first and third bit signal is near zero. But in case of the moving target, like this, first ramp bit signal and the third bit signal is like this, different, very different. And finally, we get the difference between the dual chop signal. We get the like form the sinusoid. We simulator shows the simulator result. First, detection performance. We consider third target. Four target. Only one target is stationary. Three target moving. This is the simulation parameter. Center frequency and bandwidth like this. This is the FMCW waveform. And target distance and speed like this for target. You can see the simulation result. 3 feet you can see. This is the moving target, and except for the stationary target. And another simulation result from the viewpoint of the statistical analysis. This is the distance accuracy. And in two cases, we consider two cases. One is the high variable amplitude with beta signal, chop signal, and the low variable beta signal. X-axis is the SNR, the y-axis is the RMSE. You can see as SNR is increased, as expected, the distance is the higher, gets better in both the high and lower variable amplitude. We made various experiments to evaluate the performance of the proposed algorithm in surveillance radar. We make the radar platform for the surveillance application. This is the block diagram, and this is the polar graph. This is the antenna picture. You can see this is the transmit antenna, and this is the two-channel receive antenna. And this is the back-end module picture. You can see this is the MCU and the external memory. This interface is connected between the front end and the back end module. We first made the experiment in the clean environment in anechoic chamber. This is the no noise and the no clutter environment. This is the sophistications is the anechoic chamber. We consider the three target. This is three target. And two target is the stationary. And one target is the moving. You can see is the one fixed. This is corresponding to the moving target, positioned at the about 5 meters. And this is the angle detector. Only one moving target among the three obstacles can be well detected because of the one fig in temporal and spatial spectra. We made experiment for the in single person and multiple person in indoor high clutter environment. This environment have very reflected from the wall and the many multiple stationary obstacles, metallic obstacles. And this person is the moving go out from the radar by the two different working mode. One is the slow mode, in this case normal walk, and another case is the fast mode, like jogging. You can see the experimental result. X-axis is the frame index, the y-axis is the detected range. You can see the move. This slope is the velocity. This case is the slow mode, just walking, normal walking. This is the jogging. And finally, experiment for the two-person working. This is one person is the approaching to the radar, and the other is the going away from the radar and crossing. Two person is the crossing. And this is the two target detected. And this is the range trajectory. Two persons is crossing. You can see. The proposed algorithm can detect only one moving person, and also the multiple person. Under this is the a highly cluttered environment, including the many stationary targets. I will conclude that we proposed and implemented a low complexity FMCW radar algorithm using dual chops for surveillance applications. In order to overcome the complex problem in convention surveillance FMCW radar algorithm, the difference between two chopped bit signals is utilized instead of the all chopped in conventional approach. In order to verify the conventional performance of the proposed scheme, we simulate and made an experiment, an indoor and real experimental environment. According to the simulation experiment, multiple target as well as the single target were detected, both in the ideal lab and the actual indoor environment, including the various clusters. Thank you for your attention.
Again, good timing. So we have time for questions. Anyone? Please.
On one of the slides, you said that your proposed algorithm manages to detect 4 targets. Do you have information how other algorithms, how many objects can they detect under the similar conditions?
Your question is how many target?
Other algorithms, not
How many objects?
objects, not your algorithm, but some other algorithms, state of the art currently. How many objects can they detect?
Yes. The number of the target to detect to be detected the same with in both the conventional and our proposed algorithm.
Okay.
Same.
Okay,
The number is the same.
Good. Any more questions? Can I ask my question?
Yes.
What confused me is that you are using word detection.
Yes.
If you are going to doctor and they
Yes.
say we will detect whether you have cancer or not, so probably you know that there are certain measures to prove that you are detecting or you are not detecting. Indication just of the speed or the distance is not detection. You have to construct receiver operating curve, and then you have to present the specificity and sensitivity or probability of false alarm and probability of detection. So what about the numbers? Yes, you said detection, but have you been evaluating the numbers? Have you been constructing receiver operating curve and providing for yourself, or maybe you can report for us, probability of detection and probability of false alarm?
Your question is what is the probability of detection and the false alarm rate in my proposed algorithm?
No, you are stating that it is supposed to be used in surveillance.
Yeah.
In surveillance, this means that you are turning on red lamp and you're saying intruder, or whatever, or you light on the light, or you switch on the cameras or lights and so on. So this means that you are detecting certain event, that somebody is in there, or occupation or presence detection. So this has to be stated with some probability values, probability of detection, and at the same threshold level, probability of false alarm. So do you have these numbers to report?
Your question is very good. I don't analyze the probability detections.
That's the future.
Yeah.
Okay, thank you. Anyone else? If not, then we can move to next presentation. And this time we are moving a bit away from the radars and fault detection, but still it is within our signal processing technologies, and it is a support agent of semi-logarithmic quantizer for Laplacian source. And presenter is Zoran Peric.
No, Sinisa Suzic.
Sinisa Suzic.
Yes.
Okay, floor is yours.
Okay. Just a second. Hello everyone, my name is Sinisa Suzic and I'm coming from University of Novi Sad, Faculty of Technical Sciences from Serbia. And the co-authors of my papers are from University of Niš, Faculty of Electronics. These are Professor Zoran Peric and Nikola Simic, and also this is my dear colleague Tijana Delic. She is also from Faculty of Technical Sciences from Novi Sad. In my presentation, I'm first going to make a short introduction about the quantization and something more about the compounding quantizers, and then the second part of my presentation is dedicated to construction of a semi-logarithmic quantizer and our proposed iterative and closed form solution for finding the optimal parameters of this quantizer. As we all know, quantization is one of 3 steps in the process of signal digitization. So it actually does the discretization of input signal amplitudes. It consists of 2 phases. The first phase is encoding, and actually we split the range of real numbers to some cells, and then the output of the encoder is actually the ordinal number of the cell to which the input amplitude belongs to. And then we have the second part, it's decoding part, in which we actually convert this ordinal number of our cell, or the output of encoder, to some real number value. So we can define the transfer function of our quantization process as given on this formula. And usually we describe the performance of quantization by the mean square error that we call the distortion. And it's calculated as the error of the difference between the input signal amplitude and the output amplitude of the decoder. And in this formula, P is actually the probability function of the amplitude of the input signal. But usually, except the distortion, we also define the signal to quantization signal to noise level. Of course, we want to achieve that this value is as low as possible, and contrary that signal to noise ratio as high as you can achieve. Compounding quantization is actually the non-uniform quantization, because in that process it uses the unequal cells of unequal width in that encoding phase. Why it is good? Because it can achieve the lower distortion values for the same number of quantization level, or contrary, it can achieve the same distortion using some lower number of bits. So compression of input signal is achieved. Compounding quantization consists of 3 steps. The first is the compression of the amplitude of input signal. Then on that compressed values, we actually do the standard uniform quantization. And of course, this third part is actually the decoding part. So we do the inverse. First, we do the inverse transformation to the signal range compression. One of the 2 standardized functions is actually the semi-logarithmic quantizer, which is given by this formula, and one realization of this function is given at this figure. So so this function is linear around 0, and then we have this logarithmic compression when the positive values are getting higher and when the negative values are getting lower. This compression function is described by 2 parameters. One is this parameter A, and second one is this parameter X max, which actually they detect the border between the linear and logarithmic part, and this actually this X max parameter is called the support region threshold. So in the process of quantizer construction, we assume that the probability of amplitude of input signal is described by the Laplacian distribution, and that the value of its sigma parameter is set to 1. And then if we apply that formula that are given on one of the initial slides, the overall distortion is actually calculated by summing these 2 factors. First one is granular distortion. It's actually describes the error for the amplitudes that belong to this support region, and then we have overload distortion, which actually describes the errors that are outside the support region of our quantizer. So when we start to use these equations these 2 equations from the previous slide, we get some fancy formulas that are written on these slides. And the granular distortion actually consists of 2 parts. These are DG1 and DG2. The corresponding formulas for finding these are given in this red square, and also the formula for calculating the overall distortion is calculated by this second squared parameter. And if we can see that overall distortion is actually influenced by both of these parameters, so support region threshold as well as the parameter A. And actually by decreasing X max, we are increasing the granular distortion, but on the other hand we are decreasing the overall distortion, and also by making the value of parameter A higher, we decrease the signal to noise ratio. So here are given some examples of signal to noise ratio for the different number of quantization levels and different values parameter A. And I will say later a bit how did we calculate the optimum value, since we don't know the exact X max. That is something that we want to calculate. So our goal is to find the value which minimize the distortion or maximize the signal to noise ratio. How we do that? But we need to find the value in which the derivative for X max has the value 0. But when we find this derivative, we can conclude that there is no closed form solution. So the solution that we are actually proposed, and as we investigated in the literature, there was no other proposition for some closed form solution. So we first started from iterative procedure based on the results that are obtained after this process, and we propose using this formula. this iterative formula. And also this C1 is actually only part of this equation, and it's written here not to complicate that the equation here too much. So for iterative procedure we need to know two things. First one is we need to set initial value for x max, so the starting value of our algorithm, and second one is the how to find the stopping criterion. So we define the stopping criterion when the difference between two consecutive values for SQNR is lower than 0.005 decibels. And on this graph you can see the results for different number of quantization levels, and also for different values of input. So x in, actually this means is x max input value. And we can see that for all of these cases, only after one iteration our solution starts to converge, and that this initial value is highly influenced by the choice of x in. And even if we choose the x in to be much as 10 or 12, then our first, so the first calculated value is almost equal to the convergence value. So because of this property that for higher values of x max we obtain almost near optimal values, so we propose the closed form solution where the only factor and this formula can be used when the x in has the values for 10 or 12, so based when so if we check these or these, so this formula start to converge. And inside our paper you can find two big tables where the values for optimal x max and also optimal based on the iterative procedure, based on closed form solution that we proposed, and optimal solution. Optimal solution is actually achieved by doing the some numeric calculations. Here are only the parts of these big two tables. So we calculated the relative error between optimal solution and iterative procedure. It's this index 1 in these deltas. Index 2 is for closed form solution, and we also here are given the values for signal to noise ratio, both for iterative procedure and for closed form solution. So as we can see, the results are given for different number of quantization levels for different values of parameters A. And then we can see that the relative errors for almost all cases for this iterative procedure are lower than 1%. Of course, for closed form solution, they are a bit higher, but also for many cases not such high, while the errors for signal to noise ratio are all under 1%. So in this short presentation, in our paper, we analyze the sum performance of semi-logarithmic quantizers. We give the optimal values for different values of parameter A and for different set of bit rates. It actually means the different number of quantization levels. And we have also proposed some iterative solution for finding the optimum value of x max or support region threshold, and also proposed closed form solution. We gave some results that state that the errors introduced by these two proposed solutions are not too high compared to more complicated numerical solution. Right in time, I think.
Congratulations. Okay, we have time for questions. No one? Then I'd like to ask mine.
Of course.
what confused me is that, did I get you right? Is that instead of after sampling,
Yes.
after quantization, instead of storing the number as you got it, you are compressing the dynamic range.
Yes.
For what reason?
Because from statistically, when majority of signals are examined, the majority of values are in the near the zero, and the probability of those that
So
are,
you are assuming Gaussian distribution or something similar?
yeah, something similar, and that the overall results are so why this compression can be achieved, because the overall error when because we are linearly using near the zero, we won't affect
You want to
these.
store that
Yes,
information
but
as good
though-
as possible,
yeah,
but
at the end, so if we make that error, so it's not so problematic if we use compression of these border cases.
okay, thank you.
Okay.
More questions? I have one more question. This time is this is related to compression, because what you are trying to do to save the amount of the data that's supposed to be transmitted later on, because what is the reason that you are trying to compress those edges? You are trying to compress the data so there will be less bits to transmit. But there are two techniques to reduce the amount of the data transmitted even further. One is quite simple. You just analyze the statistics of the signals that you are getting, and then you change the coding. Instead of transmitting 0 as 0, 0, 0, 0, 0, you transmit it as 1 bit. Then the values of the amplitude that repeat most frequently, you transmit with very short bits, and the ones that are very rare, you transmit with very long bits. That's one. And another one is, it is coming more and more, it is compressed sensing. So in case of voice coding, compressed sensing means that you are modeling the tongue, the teeth, and so on. In case of video, you divide the video into rectangles and you are trying to predict, and then you are transmitting just prediction function. But in general sense, what we have seen in case of cardiac monitoring in radar, they just have the model for the signal that is present. Of course, it depends on application. For cardiac one, for radar another one. They fit that model, and what they are transmitting is just the parameters. Why you went into this approach? Because it is just general, because probably any signals that one will take, they will look like Gaussian distribution or triangular distribution, or there were another reasons for choosing such type of compression?
So there were no some special reasons. So we just analyzed when we realized that there are no solution for this problem that we had. But also, I'm into the field of speech synthesis, and I know about all of these models. But mainly, when we are making these models by modeling, so we are making some bigger errors than using this standard approach. Okay, these are vocoders. You can understand everything when it's decoded, but still the spectrums are not the same, and you can there are some slight differences. Yeah, of course.
Okay, thank you.
Oh.
Congratulations. So the last presentation is coming instead of the one that has been planned. It is coming from electronics section, but still it is more or less in our field, but because it sounds like control of AC DC modular multi-level controller, and
Converter.
the presenter is Wojtek Blankic.
Okay, I introduce myself.
Okay, please. floor is yours.
My name is Wojciech Blachnik, and I'm come from the Czech Republic, and University of West Bohemia, Faculty of Electrical Engineering. This research we with our colleague preparing for our industrial partner and on our Regional Innovation Center of Electrical Engineering. This is my presentation outlines and the first, the motivation. With our industrial partner Škoda, we preparing new solution for a locomotive new generation with medium frequency transformer, and there is a necessary use a frequency converter for change frequency to medium frequency. This converter is connected directly to trolley wire. In this case, single phase trolley 25 kV. We choose a frequency indirect frequency converter. Based on modular technology. We use a H-bridge cell, which are connected in series, and we have the modular voltage and medium high voltage on the AC side. This converter provides medium or high voltage on the AC side, and during the modulation technique it's possible switch between just two levels. In this case we have 3 power cells in series, and in the finale we have 7 different voltage levels on the AC side. Because we use a phase shifted PWM modulation technique. This is our laboratory prototype. We tested on this prototype. It consists of input 7-level cascade 8-bridge active rectifier. And each of these H-bridge is possible loaded by controlled load. And now a few words about the control of this converter. The first part is voltage synchronization. Second part it's current control. There's a voltage control and voltage balancing part. The voltage synchronization is based on SOG PLL voltage synchronization. This part provides interference resistance. The important part are these integral blocks there. And now this is PLL hooking under voltage connection. There is possible speed up by preset some nominal values. What is important? The frequency of the trolley wire voltage is not constant. There is some fluctuation, approximately from 48 to 52 Hz. It's possible. And we tested our synchronization for step change from 50 to 48 Hz. The second part is a control of the current control. It's based on a resonant controller. We use a resonant controller for fundamental parts of the current, and also 2 resonant controller for third harmonic and 5th harmonic compensation. we use an adaptive resonant controller with advanced sinus limiter. It's a resonant controller where is possible change the fundamental frequency of the current because it depends on the fundamental frequency of the voltage, trolley by voltage. And the output it's with the adaptive with the sinus limiter where we have a saturation limit, and after the change of the input signal there is necessary immediately decreasing. It's like for the standard PI controller where it's possible the saturated P part and I part. And now some words about the control of the current. The green one is the current. It's a low ripple and it's a harmonic during the fine current control. There is a possible the harmonic current during some specific trolley by voltage distortion. And now a few words about voltage balancing. We use voltage balancing, which is based on capacitor energy voltage calculation, and we computed the modulation signal for each H-bridge separately, and the ratio is changed during one period. And this is the results for voltage balancing under non-symmetrical load. The balancing is during 2 periods. And however, during non-symmetrical load, the current ripple it's not low ripple like a symmetrical load. There is a current more ripple, and it's caused by the voltage not switching between 2 levels, and there is a possible 3 or 4 levels, and in the final the current it's more ripple. In harmonic analysis it's for the symmetrical load, whereas the parts of the 6 kilohertz. However, during non-symmetrical load, there is a component for the 2 kilohertz and 4 kilohertz, and the problematic can be the 2 kilohertz components part, because it's a part which is necessary compute for the THD according EMC grid standards. And now selected experimental results of the control of the converter during change of the frequency from 50 to 51 Hertz. It's a step change. However, during the standard, during the operation, it's more slowly, approximately 1 Hertz per second. And during step change of the trolley voltage from 230 to 207, it's the control step function. However, the natural multilevel is changing. And the conclusion, the important part of conclusion, it was the harmonic distortion. There is a necessary during non-symmetrical load, the 2 kilohertz harmonic components, it's problematic, and for the calculation THD for EMC with standards, and about the control and I talking. Now, thank you for your attention, and your questions are invited.
So, are there any questions? May I?
Okay.
Can you go to, I don't know, slide maybe 3, where it was indicated what was the line voltage? Somewhere at very, very beginning. Yes. No. Yes. What is this 25 kilovolt?
It's a traction rate.
Yeah. But your design concerns this primary converter. But 25 kilovolts, and I've seen MOSFETs in your design.
No, it's not. It's IGBTs for
Yeah, even
6.5.
IGBTs. But maximum voltage for IGBT.
6.5 keys. And there is a connected necessary. This is a laboratory prototype. In the final application, is there 10 or more, 12 connected converters,
I see.
and we just tested because the final power it's approximately 6 megawatts. And we tested on.
No, I have already understood why
okay.
it is this. Thank you. One more question. When it comes to the application or approach that you are proposing, is it aimed to reduce the harmonics, or it is the side effect because you reported that there are high harmonics? But are you aiming to do the power factor correction? What is the main reason that you are doing this topology?
The main reason is this medium frequency transformer. And there is a necessary change in the frequency.
Because my question was, what will happen if all the trams that are running on the same line will do this? Because now you are assuming that the input voltage is sinusoidal. If everybody will start distorting, it will not get sinusoidal.
Yeah, it's a good question. Sometimes the voltage in the trolley wire, it's a ripple. Yeah. And there is ripple by specific harmonics, that 5, 7, and it's a reason for our compensation, that and 5 harmonics.
So you are planning to deal?
Yeah.
Okay. Thank you. Congratulations. So thank you everyone who contributed. Thank you for everyone who attended. Now you have earned that. Coffee break.